Welcome to the Deep Dive. Today we are strapping in for quite an architectural tour.
Yeah.
It's really changing how developers are thinking about artificial intelligence these days.
Yeah, absolutely. For years, AI basically meant one thing, didn't it? Dependency.
Totally. Sending your data, often really sensitive stuff, off to proprietary cloud services. You sort of surrender control and, well, you end up with a pretty hefty bill you can't really manage.
Exactly. And we're seeing this massive strategic pivot now across the board, really. The core mission of this deep dive is moving decisively beyond that whole dependency model.
Okay.
We're talking about taking back control, maximizing data privacy, which is huge, and, radically increasing efficiency by running these large language models, the LLMs, locally.
Right on your own hardware, or maybe in your company's private cloud setup.
Precisely.
Okay, so let's unpack this. We've looked at a stack of really great source material detailing, like the modern toolkit for developers wanting to host their own AI. This isn't just theory, is it? This is the real nuts and bolts of self-sovereign AI infrastructure.
Yeah, our scope here is pretty broad, but it's sharply focused on the how. On implementation, we'll look at the foundational tools, the ones that make simple local execution even possible, specifically Ollama.
Ollama, right. Heard a lot about that.
Then we'll move into the, high-performance techniques you need for production scaling. That means diving deep into vLLM.
Okay.
And crucially, we'll explore how you get good answers, the role of advanced knowledge retrieval using RREG strategies. And that includes the necessary step up to hybrid retrieval.
Hybrid retrieval, got it.
And finally, we need to tackle how you standardize the tools these AI agents use. That brings us to the Model Context Protocol, or MCP.
Okay, so our goal for you, the listener, isn't just to hear about the strategy, privacy, cost control, independence, all that good stuff, but also the deep technical underpinnings.
Right. We want you to really grasp concepts like, say, how PagedAttention is kind of like virtual memory in an operating system.
Or how Ollama's model file is a bit like a Docker file for your AI model.
Exactly. By the end of this, you should know the practical steps to actually architect and implement powerful private AI infrastructure.
All right, let's jump right in. Why this whole movement? Why local execution right now?
Yeah.
So why the sudden kind of intense obsession with pulling these massive, complex models off the big cloud platforms and onto, developers' laptops or local servers? What's the main driver here?
Well, it really starts and ends with control, particularly around data. The absolute paramount benefit, the non-negotiable one, is privacy and control.
Okay.
When you run an LLM entirely within your environment, your laptop, your server, your company's private cloud, all the data stays right there. The prompts you send in, the answers you get back, everything.
That is huge. I mean, especially if you think about regulated industries, right?
Finance.
Healthcare.
Defense, yeah, exactly. You're fundamentally ensuring that sensitive client data or internal company data is just never transmitted across the public internet. It's not stored on some external provider's infrastructure.
Right. And that solves a massive security headache straight away. And a regulatory one, too. That often just blocks AI adoption completely in those sorts of places.
Precisely. For, the compliance officers, the CCOs, this is often the deciding factor. It shifts the liability, the compliance burden back to the organization itself where they can actually manage it.
Makes sense.
And tied right into that is the huge gain in independence. Developers get protected from all that volatility you see with cloud services.
You mean like sudden API policy changes?
Yeah.
Or rate limits that just appear overnight?
Yeah. Or even availability issues. Your whole application could just stop working because a major cloud provider decided to change something. With local execution, you decouple your app's stability from the vendor's stability. You're in control.
I can definitely see the long-term business case there.
Yeah.
But let's talk money. Cost. If I'm running a powerful model on my own GPU, well, that hardware isn't cheap. So where does this cost control and efficiency claim come from?
It's about shifting how you think about the cost. It's an operational shift, really, from ongoing expense to capital expenditure.
Okay, so OpEx to CapEx.
Exactly. Yes, the initial hardware cost is real, but running it locally eliminates those ongoing metered costs you get with cloud AI. Those per token fees, especially when you scale up, they can become punishing and often unpredictable.
Right.
By owning the inference cycle, you basically convert that variable operational cost into a fixed capital cost.
Right.
Plus, think about the development life cycle. prototyping, testing.
Yeah.
You cut out all those steps of requesting, provisioning, and then paying for specialized external hardware just to try something out, like a proof of concept, a PC. You can prototype right on your laptop. That speeds things up significantly.
Okay, that makes a lot of sense. The cost is fixed, predictable, not this runaway variable expense. And that brings us to how this actually works day to day. Our sources had a great analogy for this.
Yeah, the local database one.
Exactly. Running an LLM locally through a standard API, typically on, localhost door 11434.
That's
It's basically just like talking to any other local service, like a Redis cache or your local Postgres database. It's just part of the infrastructure you manage.
And the tool that has really single-handedly made this popular, made it accessible, is Ollama.
Right.
Ollama is the foundational command line tool, the CLI, that just abstracts away all the underlying complexity. It simplifies that whole process.
Yeah.
Installation, managing different models, running them on your machine, Mac, Windows, Linux, it covers them all.
I remember the dark ages before Ollama, trying to set this stuff up.
Yeah.
It was painful. Downloading weights from Hugging Face, fighting with runtimes, dependencies, specific CUDA versions.
Oh, tell me about it. It wasn't development, it was dependency hell. I think I once spent like 3 solid days just trying to compile PyTorch with the exact right CUDA version for a specific GPU driver.
Yeah.
Nightmare.
Yeah.
Ollama just streamlines all that down into one core command, basically. Ollama run model name.
Okay. Ollama run and then the model name, like Llama 2 or Mistral. Looks simple. But what's actually happening under the hood when I type that?
Right. It looks simple, but it kicks off a crucial 2-step process. First, it does a pull, a download. If you don't have that specific model on your machine already, it fetches the prepackaged version from the Ollama repository.
Okay, so it gets the model files.
Then second, and this is the key part for integration, it starts a server. It launches this lightweight local inference server that's instantly ready to accept standard API requests on that port, 11434.
Okay, so even when I'm just typing questions into the terminal right after running that command, I'm not directly talking to the model. I'm actually sending like HTTP POST requests to that local server.
That's the key technical insight. Yes, every single interaction, even that simple terminal chat, is routed via that standardized local API endpoint.
But wait, if everyone's standardizing on the same local port, 11.14.3.4, doesn't that create like a new security risk? An easy target for malware on my machine looking for that predictable endpoint.
That's a really critical point, especially for production. And the sources do address it. Because it is local, the argument is that it's easier to control using standard tools.
Like a local firewall.
Exactly. Or binding the service only to the loopback interface, 127.0.1, so it's not listening on your main network connection at all. The risk is managed locally on your terms rather than being globally exposed.
All right.
And to make all this powerful stuff actually run on, normal hardware like a laptop, Ollama relies heavily on a couple of key technical concepts.
The first one must be quantization.
Right.
That sounds essential for fitting these things onto limited hardware.
Absolutely essential, yes.
Yeah.
Quantization is basically a compression technique. The models you download via Ollama are typically quantized. Their weights, the numerical values, have been compressed.
How does that work? Reducing precision.
Exactly. You reduce the precision, maybe going from, say, 32-bit floating point numbers down to something much smaller, like 4-bit integers. You'll often see formats like Q4K mentioned.
Okay.
This compression drastically reduces the memory footprint. It allows maybe an 8 billion parameter model, which sounds huge, to actually run on hardware with limited VRAM while hopefully keeping most of the accuracy.
So without quantization, running these powerful models on a regular laptop would just be impossible.
Pretty much impossible, yeah. You'd hit the VRAM limits instantly.
And what's actually running these compressed models efficiently across different kinds of hardware? CPUs, GPUs?
That's the optimized backend. Ollama uses runtime engines, like the very popular llama.cpp. These are specifically built to execute these quantized models efficiently, not just on high-end NVIDIA GPUs, but also leveraging regular CPUs, even the integrated GPUs you find on Macs with Apple Silicon.
And how does llama.cpp manage that? What makes it so efficient?
It really focuses on heterogeneous acceleration. It uses highly optimized, low-level code kernels that talk directly to the hardware. Things like Apple's metal shaders or specific CPU instructions like AVX. It optimizes matrix multiplication, which is the core math of LLMs, and manages memory really carefully. That deep hardware access is key for speed on consumer gear.
Okay, so we've got the model running locally efficiently. Now let's talk about the Ollama model ecosystem and customization. It's not just running one or two big names, right? The repository seems pretty diverse.
Oh, it's a really vibrant ecosystem now. You've got the big foundation models, sure, from the major labs, but just as important is the growing range of specialized models.
Meaning models trained for specific tasks.
Exactly. Developers aren't just downloading general chatbots, they're pulling models fine-tuned for things like code assistance or dedicated embedding models just for turning text into vectors for search, vision models, even highly specialized tool calling models, which are essential for building complex AI agents.
Right. The sources highlighted one example, the IBM Granite 3.1 model. What makes something like that enterprise ready beyond just chatting?
Yeah, Granite gets called out because it's built with enterprise needs in mind. It has strong multilingual support, I think up to 11 languages, which is crucial for global companies. And importantly, it's specifically optimized for two advanced use cases.
Which are?
RAG, retrieval augmented generation. So it's good at using external information you feed it. And also sophisticated agentic behavior, meaning it's designed to intelligently choose and use external tools or functions.
Okay, agentic behavior. We'll definitely come back to that with MCP later. But first, customization. What if I have my own fine-tuned model, maybe trained on my company's internal documents? Or I need to lock in a very specific personality for my AI.
That's where the model file concept comes in. You mentioned it's like a Docker file, and that analogy is spot on.
So it's like a recipe for my specific model configuration.
Exactly. It's a declarative blueprint. You can use it to import existing model weights, maybe from Hugging Face. You specify the base model you're starting from, set parameters like temperature or context window size. And crucially, you define permanent system prompts.
Ah, so instead of trying to engineer the perfect prompt every single time I make a request.
Right. You define it once in the model file, something like, you are a meticulous legal assistant, always cite 3 sources for every claim.
And that instruction just sticks.
It becomes a persistent foundational instruction for the model. It gets processed before the user's actual query, setting the stage, defining the persona, the rules of engagement. It overrides whatever the user says later in terms of core behavior. That's critical for building reliable, domain-specific applications, not just toys.
That level of control sounds key for making this production ready. But the real work starts when we connect it to our applications. Let's talk about integration with standard development frameworks. The sources used a Java example. If I'm a Java developer, I probably don't want to be making raw HTTP calls to localhost.111.434, right?
No, definitely not in a large application. It's messy, error-prone, and locks you in. You need a robust standardization layer, and that's where frameworks like LangChain come into play. For Java specifically, LangChain 4j.
What does LangChain 4j do?
It provides this unified API wrapper. It abstracts away the low-level communication, so talking to your local Ollama server looks and feels exactly the same in your code as talking to the OpenAI API or Azure OpenAI.
Ah, so you can swap the backend local Ollama, remote OpenAI, without rewriting your application logic.
Precisely. That abstraction is incredibly valuable for flexibility and future-proofing.
Let's walk through the demo scenario they used. The parasol insurance use case. That sounded like a really good practical example.
Yeah, it really highlights using local LLMs for sensitive data. So Parasol Insurance, this fictional company, they process new claims. These claims are full of unstructured text, sensitive stuff, medical details, financial info, personal accounts.
All right.
They use a local LLM running via Ollama to basically ingest and summarize this claim information automatically. The goal is to speed up decision-making by having the AI quickly pull out the key facts, risks, maybe inconsistencies.
So the app isn't asking the LLM to, like, write a poem about insurance. It's sending structured data claim ID, dates, the claim text itself.
Exactly, a structured input. And asking for a structured output back. Maybe a summary focused on high-risk factors, formatted as JSON with specific fields like severity score or summary discrepancies.
And LangChain 4j handles bridging that gap.
Yes. It takes the Java claim object, packages it into the right JSON format for the Ollama API, sends the post request, gets the response, and parses the structured JSON output back into something the Java application can easily use. And crucially, all that processing, all that sensitive claim data, never leaves their local network.
And the setup for this, the configuration in the application, seemed almost ridiculously simple.
It really is, considering the power you're unlocking. The key configuration detail is often just one line in a config file, like application.properties. You just set the base URL, quarkus.langchain4j.lollama.base-url http.localhost.11434.
That's it.
Or pretty much. LangChain 4J handles the rest. Often, it'll use something like a WebSocket connection under the hood for efficient token-by-token streaming of the response back to the application. You get powerful AI capabilities without that data privacy risk.
Okay, switching gears now. From enterprise Java to maybe faster prototyping scripting, what about simplified Python development? The sources mentioned libraries like Checkr promising a two-line approach.
Yeah, Python developers often look for maximum abstraction, right? Speed and simplicity. And that two-line approach is basically what it sounds like. Line one is importing a function specific to your local model, like from Chuckalm, import Askalama
So the library already knows you're using Granite running via Ollama locally.
Exactly. And line two is just calling that function with your prompt, print Askalama, who was Ada Lovelace.
And all the setup, the connection, the API call, the JSON formatting, that's all hidden.
All handled by the library in the background. It's super convenient for quick scripts or basic tests, but for a real user interface, you hit that latency problem again. Waiting for the whole answer can feel slow.
Right. You want that text appearing word by word or token by token like ChatGPT does.
Precisely. For a good user experience, you absolutely need streaming for responsiveness. And in Python, that usually means using asynchronicity, typically with Asyncio.
So you switch to a different function call.
Yeah, you'd use the streaming variant, maybe something like stream Ollama, and then you use an async for loop to iterate over the response chunks as they arrive from the server, printing each one immediately. It makes the application feel much more responsive, less laggy.
Okay, makes sense. What about conversation history? If I tell the model something like, my name is Chris and I'm learning Python, and then ask, what am I learning? It needs to remember the first part, right? How's that handled simply?
That's managed through context management, often using a Python context manager. You might wrap your interactive session in something like async with conversation, specifying the local provider and model.
And that conversation blog handles the memory.
Yeah, it does the plumbing automatically. It collects the user's input and the model's responses from previous turns in that conversation, and then automatically includes that history with every new request you make within that block. So the model gets the context it needs, who Chris is, what he's learning, to answer follow-up questions coherently.
Clever. And finally, just like the model file lets you set a permanent personality, can you do that dynamically in Python code too, using system prompts?
Yes, absolutely. The function calls usually provide a system prompt parameter. You can pass a string there that acts as that ongoing instruction, that persona.
Like the example they gave.
The pirate one. Yeah, that's a fun one to show to control. Pass in system prompt. You are a pirate called Jolly Roger, and you always speak in pirate speak.
Okay.
And then every single answer from the model for the rest of that conversation context will be filtered through that persona. It overrides the user's input style. It's a powerful way to shape the output consistently within your application logic.
Okay, so we know how to run a model privately using Ollama and how to talk to it effectively using standard frameworks in Java or Python. But now we hit a really critical point. Factuality. How do we make sure the model isn't just making stuff up? That brings us squarely into ARG, Retrieval Augmented Generation. And the reliability of ARGs seems to hinge entirely on the retrieval part, right? Getting the right information to the model in the first place.
Absolutely. This is the crux of building reliable, trustworthy AI systems. In RAG, the quality of the final answer the LLM generates is completely dependent on the quality of the document chunks you retrieve from your knowledge base.
Garbage in, garbage out, essentially.
Exactly. If you retrieve irrelevant chunks or outdated stuff or factually incorrect information, the LLM, even a great one, will likely generate a response that's wrong, misleading, or just plain fabricated, what people call hallucinations. So the importance of retrieval cannot be overstated. We have to make sure we're retrieving relevant, factual chunks.
Okay, so let's break down the strategies. The sources started with the classic, the old-timer, sparse retrieval.
Yeah, sparse retrieval. It's the speed king, really. The underlying techniques have been around for like 50 years. Its mechanism is based entirely on classic keyword matching and statistics about word frequency.
Like TF-IDF. Or BM25.
Exactly those. TF-IDF, BM25. It basically treats text as a bag of words and scores documents based on how often specific query words appear in them, adjusted for how common those words are overall. Simple, efficient indexing.
But wait, if it's that old and just based on keywords, why are we even talking about it? Isn't modern dense retrieval just better in almost every way?
That's the million-dollar question, isn't it? And the answer is, it depends. The pros of Sparse are undeniable. It's super scalable, incredibly fast, and really cost-effective. Why? Because you don't need complex, expensive embedding models or vector databases, just standard inverted indexes.
Okay, fast and cheap. But the downsides?
The cons are significant. It has zero understanding of semantics or context. If you search for automobile, it won't find documents that only mention car. It can't handle synonyms or conceptual similarity at all. If the exact keyword isn't there, it fails.
So why use it?
Because sometimes that weakness is actually its strength. Its ideal use cases are where exact word matches are critical, and conceptual fuzziness is actually dangerous.
Like what? Legal documents, code.
Precisely. Searching source code for a specific function name. Finding clauses in legal contracts where the exact wording matters. Searching medical databases for precise terminology. The sources stress that in highly specialized domains with unique jargon, good old BM25 can sometimes outperform fancy deep learning models because it won't confuse specific terms, chemical names, legal citations with things that are merely conceptually similar but factually wrong. It forces exactness.
Okay, I see the niche. But for most general-purpose searching, we need something smarter. Which brings us to the newer approach, dense retrieval, the semantic workhorse, as they called it.
Right. Dense retrieval has really come into its own in the last, say, 5 to 10 years. It's all about meaning, about semantics. The mechanism here is totally different. You use powerful embedding models. These are often based on architectures like sentence transformers or even specialized LLMs themselves.
And these models turn text into numbers, vectors.
Exactly. They map both the user's query and all the documents, or chunks of documents, in your knowledge base into a high-dimensional vector space. It's like giving every piece of text a coordinate in a complex geometric map.
And the idea is that texts with similar meaning end up close together in this map, even if they use different words.
That's the core concept. Similarity isn't based on keyword overlap anymore. It's based on proximity in this vector space. You find the closest document vectors to the query vector, typically using fast, approximate nearest neighbor, ANN, search algorithms, often inside a specialized vector database.
Okay, that sounds much more powerful for understanding what a user means, not just what they typed.
Definitely. The pros are its powerful context understanding and great handling of natural language queries. A user can ask the same thing in 5 different ways using synonyms and varied phrasing, and dense retrieval should still find the relevant documents because the underlying meaning vector will be similar.
But it's not perfect either, right? What are the downsides?
The cons are mainly twofold. First, it can sometimes overlook very specific rare jargon if that jargon wasn't well represented in the training data of the embedding model. The model might not understand the specific vector for that rare term very well. Second, it can be less effective for very short keyword-like queries. If you just search for BM25, the lack of surrounding context makes it harder to generate a distinct, meaningful vector. Sparse might actually work better there.
Okay, so dense is the go-to for more conversational things.
Yeah. Ideal use cases are things like general chatbots, customer service knowledge bases, searching large collections of unstructured documents where users ask questions in natural, varied language. It excels at understanding intent.
But neither sparse nor dense is perfect on its own. Sparse misses meaning. Dense commits specifics, which leads us, inevitably, to the state-of-the-art, hybrid retrieval. It seems pretty new, only really mainstream for a couple of years.
That's right. Hybrid is the latest evolution, and it's designed specifically to get the best of both worlds, to fuse the strengths of sparse and dense and mitigate their individual weaknesses.
Okay, how does it work? What's the mechanism?
It's conceptually simple, actually. You run the user's query through both retrieval systems in parallel. One branch does a classic sparse search, like BM25, to find documents with keyword matches. The other branch does a dense vector search to find documents that are semantically similar.
Okay, so now I have 2 different ranked lists of results coming back. One based on keywords, one based on meaning. How do you combine those into a single, better list? You need some kind of fusion algorithm, right?
Exactly. That fusion step is critical. You need a smart way to merge these 2 potentially very different lists. The sources detail a couple of common approaches. The simplest is probably a weighted sum.
How does that work?
You just assign a weight, a percentage importance, to each score. Say you decide semantic relevance is more important, so you give the dense score 70% weight and the sparse score 30% weight. Then you calculate a combined score for each document that appeared in either list.
Seems intuitive. But what if, say, the dense search finds a tiny, irrelevant document that happens to be very close vector-wise, giving it a super high score? Couldn't that dominate the combined list, even if the sparse score was terrible?
That's a potential issue, yes. The raw scores from different systems aren't always directly comparable or well calibrated, which leads to the second and often preferred method for fusion. Reciprocal ranked fusion, RRF.
RRF. Okay, how is that different?
RRF completely ignores the actual scores from the sparse and dense systems. Instead, it focuses purely on the rank position of each document in its respective list.
So just the rank, like first, second, third.
Exactly. The formula gives each document a fusion score based on the reciprocal of its rank, 1 divided by rank, in each list it appears in. So a document ranked #2 in the sparse list gets a score component of 12. If it's also ranked #3 in the dense list, it gets another score component of 13. These are summed up.
Ah, I see. So a document that ranks consistently high in both lists gets a massive boost regardless of what its raw similarity scores were.
Precisely. It heavily rewards documents that both systems agree are important by ranking them highly. It prevents a document that gets a single fluke high score but low rank in one system from unfairly dominating the final merged list. It's much more robust against outliers and score calibration issues.
Okay, that sounds much smarter. And the result? Does hybrid actually perform better in practice?
The impact is pretty clear across the board in recent benchmarks. Hybrid retrieval consistently and often significantly outperforms pure dense retrieval alone. By combining keyword matching for specifics and semantic matching for meaning, it improves both precision, the accuracy, making sure the retrieved stuff is actually relevant, and recall the completeness, making sure you find more of the relevant stuff that exists.
So for anyone building a serious RK system today, especially in a business context with specific terminology, hybrid isn't just an option, it's pretty much the default best practice now.
I'd say so, yeah. Its ideal use cases cover almost all serious RRAG implementations. It's particularly crucial when you're dealing with knowledge bases full of specialized jargon, think technical manuals, legal archives, medical research, places where missing a key term because dense search focused only on general meaning could be really problematic, even dangerous. Hybrid covers both bases.
All right. We've figured out how to run our model locally and privately with Ollama. We've made sure it gives factual answers using hybrid RAG. But what happens when we need to go big? Beyond just one developer's laptop into a real production environment like a fleet of VMs or a Kubernetes cluster handling maybe hundreds or thousands of requests a second, we need efficient scaling. And that brings us to vLLM.
Yeah, vLLM is incredibly important here because the traditional ways of serving LLMs, often just using standard PyTorch or TensorFlow serving frameworks, they create some major headaches in production. Headaches that cost real money and slow things down.
Okay, like what? What are the main problems?
The sources highlight 3 big ones. First is memory hoarding. Standard frameworks are notoriously inefficient with how they allocate precious GPU memory, especially for the KV cache.
The KV cache. Remind me what that is again.
That's the cache that stores the attention keys and values the model needs to generate the next token in a sequence. It grows with the length of the conversation. Traditional systems often reserve a huge, single, contiguous block of memory for this cache up front for each request.
And that's bad because?
Because it leads to massive memory fragmentation. You end up with lots of small, unusable gaps between these big reserve blocks. It wastes incredibly expensive GPU VRAM and forces companies to buy way more hardware than they actually need.
Okay, wasted memory. What's the second problem?
High latency, slow response times. This often comes from the third problem, which is inefficient batch processing.
How does batching cause latency?
Well, traditional systems often use static batching. They group a bunch of requests together, send them to the GPU, but then they have to wait for all requests in that batch to finish generating their output before they can start the next batch. If one request in the batch is generating a very long sequence, all the others that finish quickly just sit there waiting. Idle GPU time means higher latency.
Got it. And the third challenge?
Just the sheer scaling difficulty. Modern LLMs are huge. Their memory and compute needs often exceed what a single GPU can handle. This forces you into complex distributed setups across multiple GPUs or machines, which adds a ton of engineering overhead and costs.
Okay, so memory waste, high latency from bad batching, and difficulty fitting models onto GPUs. How does vLLM fix this? It came out of UC Berkeley, right?
That's right, and it was designed specifically to tackle these 3 issues head-on. The benchmarks are pretty stunning. They claim throughput improvements of up to 24 times compared to traditional serving systems like Hugging Face transformers.
24 times. That's not incremental. That's a massive leap. That translates directly into cost savings, surely. How does it achieve that? The core mechanism seems to be PagedAttention.
PagedAttention is absolutely the key innovation. It directly attacks that memory hoarding problem. the inefficient KV cache allocation. Remember how traditional systems reserve big, contiguous blocks?
Yeah.
PagedAttention does something much smarter, borrowing an idea directly from operating systems. Virtual memory.
Okay, so just like my OS manages my computer's RAM by dividing it into small, fixed-size pages.
Exactly. PagedAttention manages the GPU memory for the KV cache by dividing it into small, fixed-size blocks like pages. Instead of needing one huge chunk, the KV cache for a request can be stored in many of these small, non-contiguous blocks scattered across the GPU memory.
And how does it keep track of where all these scattered blocks are?
It uses a concept similar to an OS page table. It maintains a mapping that tells it which physical blocks hold the data for each logical part of a request's KV cache. This means memory doesn't get fragmented nearly as much.
And the big win there is?
Much better memory utilization. You can pack way more requests onto the same GPU. Even better, PagedAttention allows for sharing of these memory blocks between different requests if they share a common prompt prefix, which happens a lot. It drastically reduces the overall memory footprint. That wasted VRAM becomes usable capacity.
Okay, that page-based virtual memory approach for the KV cache sounds fundamental to their efficiency claims. That's huge for GPU cost savings.
Absolutely fundamental. And the second key mechanism addresses the latency and throughput issue, continuous batching.
Continuous batching. So instead of waiting for the whole static batch to finish,
It's dynamic, it's proactive. It maximizes GPU utilization by eliminating that idle waiting time. With continuous batching, as soon as any sequence in the currently running batch finishes generating its output and frees up its resources on the GPU.
vLLM immediately slots in a new waiting request from the queue.
Instantly. It keeps the GPU constantly fed with work. No more waiting for the slowest request in a batch to complete. This continuous filling process avoids those latency bottlenecks and directly contributes to that massive throughput increase they claim.
Makes perfect sense. And the beauty of it, for developers, is how you actually use vLLM, right? The implementation.
Yeah.
It often exposes itself as
An OpenAI-compatible API endpoint.
Yeah.
Yes, this is a brilliant strategic move.
Why is that so important?
Because it means if you've built your application against the OpenAI API standard, which tons of people have, you can decide to self-host using vLLM for cost or privacy reasons, swap out the API endpoint URL, and that's it. Your application code doesn't need to change.
Wow, that's seamless migration.
It lowers the barrier to adoption massively.
Yeah.
And just like Ollama, vLLM also fully supports using quantized models, so you can combine the efficiency of quantization with the serving efficiency of PagedAttention and continuous batching for maximum resource savings in production.
Okay, fantastic. We've covered running the core LLM efficiently at scale. But modern AI isn't just the LLM in isolation. It's often an agent that needs to interact with the outside world, call external APIs, query databases, use legacy systems. How do we standardize that communication? That brings us to the Model Context Protocol, MCP.
Right. MCP, which Anthropic helped launch relatively recently, I think late 2024, is aimed squarely at the huge fragmentation problem we have right now in the AI agent ecosystem.
Fragmentation, how?
Well, currently, basically every different AI framework, LangChain, Llama Index, AutoGen, you name it, and every different LLM provider has its own proprietary way of defining and declaring external tools.
Tools being things like an API for checking stock prices or a function to calculate mortgage payments.
Exactly. And the problem is if you define how to use that stock price API for LangChain, you have to define it all over again, likely in a different format, if you want to use it with an agent built using AutoGen or directly with an Anthropic model versus an OpenAI model. It's tons of duplicated effort.
Right. Every time I want the same tool used by a different agent framework, I have to rewrite the description and the schema. Painful.
Super painful and hinders interoperability. The MCP solution is proposing a standard protocol. The idea is you define your tool server once, conforming to the MCP standard, and then any MCP-compatible client, any agent, any framework can discover and use that tool without custom integration code.
Okay, define once, use everywhere. Sounds promising. Let's make it concrete. The sources gave a nice implementation detail using a churn prediction example. How would that work?
Okay, so imagine you have an existing machine learning model deployed as, say, a standard fast API service. This service takes some employee data, salary, how long they've worked there, maybe their last satisfaction score, and predicts whether they're likely to leave the company to churn.
Standard ML API.
Got it. To make this MCP compliant, you'd wrap this existing fast API endpoint using a helper library, maybe something called FastMCP. This wrapper turns your basic API into an MCP server that knows how to advertise its capabilities in the standard MCP format. When an MCP client asks, "What tools do you have?" this server responds with a standardized description.
And what's the absolute key piece that lets the LLM agent understand what this churn prediction tool does and how to call it without needing a human to write specific code for it?
The doc string. It sounds almost too simple, but the Python doc string of the function that wraps the API call is utterly vital in MCP.
The documentation string.
Yes.
Really?
Because that docstring serves a dual purpose. It's human-readable documentation explaining clearly what the tool does, predicts employee churn probability based on input features, but crucially, it's also structured in a way, often using specific formats or type hints within the docstring that acts as the machine-readable schema.
So the LMM agent reads the doc string to figure out what the tool does, what parameters it needs, like a list of dictionaries with keys, salary, tenure, satisfaction score, and what format the output will be, and maybe a JSON with a churn probability field.
Precisely. The LLM uses that docstring metadata to automatically generate the correct JSON payload needed to call the tool correctly. The developer writes good documentation, and that becomes the API schema for the AI. It's really elegant.
That is clever. And how do you make sure you've written the docstring correctly and the whole thing works before deploying it?
You use the MCP inspector tool. It lets you test your MCP tool server locally.
How does that work?
You typically run your MCP server locally, maybe using Stadio standard input-output as the communication channel just for easy development testing. The inspector tool then acts like an MCP client. You can manually send it a test request, perhaps describing the tool you want to use and providing sample input data, like a hypothetical employee's details. The inspector shows you if your server correctly understands the request, calls the underlying FastAPI function, gets the prediction, and formats the response according to the MCP standard. It verifies your definition end-to-end.
Okay, so you test it locally, confirm the LLM can understand the docstring, and call the tool via MCP. And the ultimate vision here, the goal, the sources used a German phrase.
Your Zelbus server, MCP überall. Yeah. Meaning the same server, MCP everywhere.
That's the interoperability principle, right?
Yeah. Exactly. A tool defined once using MCP, like our churn predictor, should then be seamlessly usable by any MCP compliance system. An agent running locally with Ollama, a more complex agent orchestrated by LangChain in the cloud, maybe even a specialized code editor like Cursor that integrates AI assistants. As long as they all speak MCP, they can all use the same tool definition without custom wrappers. That standardization is what could unlock much more complex, capable, and manageable AI systems built from reusable components. #outro prop.
Wow, that was quite a journey. An incredibly detailed deep dive into the architecture of self-hosted modern AI. We started right at the foundation, didn't we? The desire for privacy, for independence, which tools like Ollama make real by letting us run powerful models locally with simple commands and those customizable model files.
Yeah, and then we tackled the critical issue of reliability, making sure the AI isn't just fast but factual. We saw how knowledge retrieval has evolved and why hybrid ARG, that smart fusion of old-school keyword search and modern semantic understanding, is really the definitive way now to build RAG systems you can trust, especially when dealing with your own specialized data.
Absolutely. And then we scaled up. We looked at the production side. First, with vLLM, understanding how really clever techniques like PagedAttention, mimicking virtual memory, and continuous batching can give you those massive throughput gains, saving serious money on expensive GPUs.
And finally, we tied it all together with the need for standardization in how these AI agents interact with the real world, with our existing systems. The Model Context Protocol, MCP, offering that promise of defining a tool once and having it usable everywhere by any compatible agent.
It really paints a picture of a powerful shift towards more decentralized yet high performance and standardized AI architecture.
It really does. And, we've detailed how to run the AI, how to scale it efficiently, and now how to define the tools those AIs use with this new level of precision and standardization through MCP. It brings up a final, maybe provocative thought for you, the listener, to consider as you start building these systems. What does this level of standardization, particularly around tools via MCP, actually mean for overall system security and auditability? On the one hand, yes, that interoperability is a massive win for efficiency, but think about it. When a single standard protocol like MCP becomes the universal way that potentially autonomous AI agents access critical production resources, maybe executing financial transactions, modifying user data, calling sensitive internal models like that churn predictor, that also creates a potentially powerful new single point of integration risk, doesn't it? If that protocol or its implementation has flaws, or if managing access control through it isn't robust enough, It's something organizations will need to build entirely new auditing, logging, and security frameworks around to manage effectively. The efficiency gain is huge, but the concentrated integration point needs careful thought.
That's a really important point. Standardization simplifies, but it also centralizes the interface, even if the deployment is decentralized. Definitely food for thought. Thank you for joining us for the deep dive.